Okay. Now it's working. Okay, great. Okay. First of all, you can hear me, right? Okay. First of all, I'd like to thank the organizers for bringing together this wonderful workshop, and it's nice to be back here in Seoul. So this work, this talk is on the eikonal, and this is going to be based on these three papers that two of which I've written with our collaborators. So one is with Johnny Kim, there's the Zhangmin Lee, who's our organizer there, and the other is with Sung-Soo Kim, so he's here taking care of the cameras. And he's actually an undergrad, so if you're looking for a grad student, you should have a chat with him. Okay, so it's been 10 years since we first detected gravitational wave directly. If you think you're seeing a deja vu, it's because Andres actually gave the introduction that I wanted to give. So thank you, Andres, because I can skip through some of the things. And we now have a huge literature on post-Minkowskian dynamics. So this is really massive. And the point that I wanted to come back to is, why did we start this? And of course, as Andres gave us the spoilers, it really goes back to Thibault's this paper back in 2017, where he asked us to compute the 3 p.m. Hamiltonian. And this was answered beautifully by our friends and colleagues, some of which are in the audience. And this is basically the two papers that sparked an explosion that became the huge PM dynamics literature that we see today. Now, since it's 10 years, 10th anniversary, I thought it would be nice to look back on the original motivations of why we started all of this. And so I decided to take some keywords from Damer's questions that to compute the 3 p.m. eikonal. So, sorry, 3 p.m. Hamiltonian. And this is really my interpretation of what Damour was dreaming of when he was asking us to do post-Minkowskian calculations. So the first keyword is effective one-body. This is just a method to resum weak field dynamics so that you get a better analytic control of the strong field dynamics, which uses the background pool limit as the leverage. And why do we want to have a strong field dynamics analytic? Because the gravitational waves that we see in the detectors are actually the strongest or the loudest in the strong field regime. The second keyword is post-Minkowskian, basically the name of our industry. And this dynamics is characterized by scattering dynamics, which we can describe using gauge invariant variables. And why is it important? Because there are relations between gauge invariant variables which may have singularities. And if we have singularities, that means there is physics behind the singularities, which we can use to do resummation. So for example, there was this L resummation that's been introduced by Damour recently, which uses the logarithmic divergence of the scattering angle as you approach the critical impact parameter. Now, having looked at the original motivations, we can ask ourselves, can you do something else? Or are there underexplored features of post-Minkowskian dynamics we can use to fulfill the original motivations? And if there is, what would be the best way to do this? And my personal answer is that we can actually look at spin resummation, and the best way to do it would be through the eikonal, which I'll be telling you about. So first thing, why would we want to do spin resummation? Because we know that spin is going to be a perturbative correction to the non-spinning dynamics. And this actually comes from the limitations or drawback, well, not drawbacks, what we have for the current waveform models. So this is a plot that I took from the analytic waveform model, which is SUV and RV5. That's been developed by our group in Boston, which is actually used in the data analysis for LIGO variable Kagra. And this is a plot where they compare the analytic model against the numerical surrogate model, which is like an interpolation of NR simulations, because we don't have NR simulations that cover the full parameter space. And on the x-axis, you see the mass ratio. On the y-axis, you see the spins. And you can see that on the equatorial line, where we don't have any spins, we are doing relatively well. But as you go to higher spins or extremal spins, as you go up or as you go down, you see that the performance is not as great. And this is also true for the binding energy. So as you go up and as you go down, you see that the disagreement increases. And this is expected to be the limiting factor if we want to do precision science for next generation aggressive wave detectors. So this is a quote that I took from one of our group's studies on systematic errors of waveform models, where they say mass distribution, we can still do it with the current waveform models, but for the spins, we probably need better waveform models. And the second question you can ask is, why do we expect to do spin resummation? And the answer is, the black holes have spin multiple structures, which are very special, and they're given by the Newman-Janis shift. So what happens is that if you have a non-spinning black hole and spin it up, this black hole splits into two. One moves in the imaginary spin direction, the other in the opposite direction. And one couples the self-dual part of the graviton field, the other to the anti-self-dual part of the graviton field. And you can regard these split particles as split point particles as the self-dual top nut that Alfredo talked about previously. And our expectation or our working assumption is that the singularities we would see in binary Kerr dynamics would be determined by this Newman-Janis shift. And if you're looking for how to do resummations, then the singularities are going to be more important than actually getting the perturbative orders in spin correct. So we can put off doing matching computations to later and worry about the singularities first. And also, this is actually possible because there are several known models which actually implement the Newman-Janis shift into the dynamics. So there's the Walsh model, and my personal favorite, which I've worked on, is twistor wall line. Yeah, it's basically what I worked on, so that's why my favorite. There are also somewhat indirect methods of implementing this. So there's the bootstrap for heavy mass effective theory, heft amplitudes. And there's also the higher spin gauge, which Uppsala group has been developing. And having an argument is not enough. I actually need to show you that the resummation is possible. So this is what we got from the second post-Lorentzian twistor wall line eikonal. So the full eikonal, when you computed it, it was actually a double infinite sum of hypergeometric functions, actually a product of hypergeometric functions, even worse. But when you take the aligned spin configuration and the double infinite sum just collapses down to a square root, you see here, which when I first got it, I thought this cannot be true. I mean, it's just too good to be true. But I did like 3 more times. It seems to be correct. And in retrospect, it's not really something that I should have been surprised, because there were previous works that studied Kerr and non-spinning scattering, which also seen the similar singularity structures. And the singularity structure actually is also seen in later works, which the Uppsala group did for the second post-Minkowskian Kerr dynamics. And another interesting configuration that I think is not actively looked into is what we call the axial scattering. So here we have the impact parameter that's lying along the direction of the spins. Here now we have elliptic integrals, which was a surprise because I've never seen elliptic integrals before in my life. And yeah, so I've told you about the eikonal, but I haven't told you what, well, I have told you about the computation of the eikonal, but I haven't told you what the eikonal itself is. And to the latest understanding of the eikonal that we have is that it's a scattering generator. So it generates scattering observable as a symmetry transform. So this is a canonical transform that it transforms the in variable to the out variable. So this was already alluded to in Ricardo's talk yesterday. And this is just a combination of K-Mock formalism with the exponential form of the S matrix with the classical limit. One thing that's been unnoticed was that we actually have a power series expansion of this eikonal matrix, and it's called the Magnus series. So we have the Dyson series that computes the S matrix as a power series of interaction Hamiltonian or the vertex rules. That is the same for the eikonal matrix. It's just that we compute it through the Magnus series. One interesting aspect of this is that this Magnus series is actually a commutator expansion. So when you compute the diagrams, you find that the graphs, if you restrict yourselves to 3 graphs, then you're forced to use causal propagators or retardant advanced propagators. And this is especially relevant if you are working in Worldline-based theories, for example, Worldline KFD. And another aspect that comes out from here is that because you're using causal propagators, all the master integrals that you use are either real valued or imaginary valued. So when you compute the eikonal, you get something that is purely real. Also, it turns out that the Magnus series gives you somewhat randomly looking combination of causal persistence for the same topology of graphs. And this actually ensures that you get a finite result for the 3PM eikonal. The second interesting aspect of this viewpoint is that we have nested brackets. So first thing that you notice is that you have commutator, well, Poisson brackets between the impact parameter. And one thing that remained unnoticed for quite a while is that the Poisson bracket between the impact parameter should not be considered to be 0. This is because you actually have to include the projection terms into the definition of the impact parameter. And the cross terms between this displacement and the projection terms is what creates this non-commutative. One feature that we found interesting is that we can actually compute Poisson brackets using diagrams. And this is what we call causality cuts. So it's basically summing over all retarded minus advanced combination of the propagators that you can join the two. And this means that we have a slightly different interpretation for how the magnitude of, well, how the eikonal works. So if you compute the diagrams that corresponds to the Magnus series, which gives you the eikonal, and if you put it into the equation that I've shown you, which I call scattering generator equation, it computes the diagrams that correspond to the impulse, which are rooted tree diagrams. And to show you, to give you a flavor of how this actually happens, these are the diagrams that corresponds to the impulse. So this one is the leading order. This one is the next to leading order. And here I've shown you the arrows that give you the causality predictions for the Worldline propagators, because that one is the only one that we need to keep track of. The other ones, the causality predictions doesn't matter because it doesn't affect the integrals. Below, we have the diagrams for the eikonal. And first thing we do is we take the diagram for the impulse. There's a causal prediction to it. We split the causal prediction into the symmetric part and the cut part, basically retarded minus the advanced part. And we see that this actually reorganizes itself into the eikonal part, which is a single bracket, and a nested bracket part. The cut part becomes the nested brackets. So in the end, what you get is the eikonal, well, the impulse organizes itself into the single bracket part and the nested bracket part. This reorganization, even though I've only shown you for the impulse, actually extends to spinning observables. And we've seen an example from Mao's talk on Monday. And one thing that I'd like to comment on here is that we can actually use Poisson brackets instead of Dirac brackets if we decide to use variables that manifestly satisfy the constraint conditions. Another comment that I would make is that these nested brackets actually act as rotations on the terms that it acts on. So the conventional understanding of the difference between the impact parameter and the eikonal impact parameter is the saddle point shift, because in the conventional understanding, we understand the eikonal approximation as the saddle point approximation of 2-to-2 scattering. Here it's different. You only have the impact parameter, and the saddle point shift is viewed as the effect of these nested brackets. And since brackets are computed as cuts, this means we can have a different perspective on the so-called K-Mach cuts that people have been scratching their heads about for quite a while, especially the people who were working on scattering waveforms. I'll comment on this a bit later. Oops. Okay. Now, second post-Lorentzian order, second post-Minkowskian order is not enough. We should actually try to test this to higher orders. So the best example is third post-Minkowskian order, which is the lowest order after that. So this is the eikonal that's been computed by different groups. We can just plug it into the equations and see what we get. And the impulse has already been computed by other groups, so we can just compare with other calculations. And what we find is that we're actually missing something. So this is the impulse that's been computed by other groups, where it has the conservative term, the radiation reaction term, and the radiation loss term. What we get from the eikonal is only the first two, and we miss the radiation loss term, where radiation loss, it's really related to the momentum that is lost by the radiation. Then we can ask, what are we missing? And when we think about it, we didn't include the graviton degrees of freedom when computing the Poisson brackets. Or in other words, when we're computing the nested brackets using diagrams, we didn't include diagrams that would come from graviton causality cuts. And we can conjecture and also show that this missing term can be computed as nested bracket that has radiation degrees of freedom inside. So to recap, the problem we had from this approach is that we didn't have vertices where we could attach graphene propagators. And the answer is kind of simple. You just add new vertices to the vertex rules. Formally, you can do this by adding or turning on the background graphene field. In practice, you just draw more diagrams with external graphene legs. Now, this gives you an expanded set of observables you can compute. So for example, the radiation loss is now computable. And you can also compute the scattering waveform and radiated energy from this extended definition of the eikonal. It also gives you a more coherent picture of why we needed the K-Mach cut contributions in scattering waveforms, which were the source of initial disagreement between post-Minkowskian and post-Newtonian calculations. So this is how you compute the radiation loss. Yeah, so this blob here is the radiation eikonal. We have two, and this wavy line with the cut is the graviton Poisson bracket. You compute it, you get the answer you wanted. For the scattering waveform, we can say a bit more. So this is what you'd get formally out of the brackets. So this would be the leading order scattering waveform, which is a single bracket. The next to leading order term would have this term here, which is the nested bracket. And because we can understand the action of the bracket as the rotation generator, this means you have a term that contributes as the rotated leading order waveform in the second order. And in terms of diagrams, they're really cuts because you have cuts here and here. So some take-home messages. Spin resummation will become important, I hope, for next generation gravity wave detectors. The eikonal, you can understand it as the generator of scattering observables, and it's actually computed by the magnet series. So you don't need to go through iterations. It's just that you have to deal with commutators. We have now a different understanding of the brackets. So impact parameter space is now non-commutative. So BB Poisson bracket is non-zero and can be computed diagrammatically using what we call the causality cuts. And we can also include radiative effects, also including the dissipation from radiated gravitons by adding graviton degrees of freedom to the phase space of where we define the Poisson brackets. Some future directions, we of course want to have something to say about the bound systems. So the question would be, can we actually do B2B continuation for non-separable Hamilton-Jacobi systems? A related question is, can we actually construct eikonal-based waveform models that we can use for bound binaries? This is a work in progress. Well, this is something that we've been thinking about for a while. Another thing related to this continuation is the problem of tail effects. So we have the problem of local in time versus non-local in time, where we don't really have an understanding of how to continue the non-local in time effects. One possibility is that this non-local in time effects are just the terms that comes from radiation eikonal, which we'll need to figure out. We'll do the calculations and figure out. One interesting thing about conceptual thing about radiation eikonal is that it doesn't forbid you from considering nonlinear versions of it. So for example, we can have the radiation eikonal, which is quadratic in the background field. And if you think about it, this is a 6-point amplitude. Now, it has been argued that 6-point amplitudes are not relevant for classical physics because they don't contribute to what was it? Sorry. Because the classical uncertainty relations, you have to minimize, and 6 points doesn't give you any new information. But when you do the calculation, when you count the powers in G, then you find out that if these things exist, they should contribute to the next to leading order waveform and the 5 PM impulse, which is the state-of-the-art calculations that people have been doing. So will they actually contribute to the classical physics? I think that's an interesting question. For the last, I've been talking about spinor summation, and I think it's important to push the limits to next to order, which is 3 PM, 3PL. And this would be the order where we first see mass ratio corrections. So it'll be relevant for doing effective on body. Obstruction, of course, is the integrals, because we know that Feynman integrals are beasts. These are monsters. They have exponential factors on top, which makes it somewhat interesting. So we've started studying mathematical structures of it with Jung-Wook there as well. And one of the things we found interesting was that some standard tools for analyzing integrals, Feynman integrals, doesn't apply here. For example, the Bykov representation doesn't seem to capture all the functional geometries behind integrals. And to the best of my knowledge, these types of integrals have first been considered by Bo Feng, and his motivation was to do tensor reduction of Feynman integrals. It'll be interesting to see if this can actually be implemented into something that's tangible. Okay, so I'm out of time. Thank you.